So hi everybody, I'm Anthony Francis. I work in the search quality department, and in a former life I was a graduate student at Georgia Tech working on making computers smarter, and it's my pleasure to introduce to you today Jim Davies, who was my colleague at Georgia Tech and now is a professor at Carleton University. Jim studies visual reasoning and cognitive science through the tools of artificial intelligence, and is the director of the Science of Imagination Laboratory at Carleton. And he's going to present a talk today on the science of the imagination. So.
Thanks. Yes, the title isn't on the slide. It's the science, a vision for the science of imagination. So I'm a scientist trying to study imagination. I'm going to talk a bit about what imagination is and why anybody should care about it. Then I'll talk about some of the theory behind it and what's been done and what could constrain imagination, how we know to do what it does. And then finally I'll talk about what I've been doing in my laboratory and what the future holds for science of imagination. So imagination is, the way I look at it is how people picture things. All right, so there are two kinds of views of imagination. The basic one is creativity, and the second is visual instantiation. So creativity, this is what people talk about when they say, for example, that somebody has a good imagination, or a story is imaginative, or somebody says, oh, I have no imagination at all. This is kind of equivocating creativity and imagination as having the same meaning. That's one sense in which we use the term. The other sense, and that's the one I'm going to be focusing on, is what I might call visual instantiation, and that is how you picture things in your head. Okay, and it doesn't have to be particularly creative. So I made eggs this morning, and if you can picture that, you might picture a stove and a floor, and I might be in my pajamas or in my clothing, and you will put things in that image that I didn't say. Okay, if I say I cooked eggs, I said nothing about a stove or a floor or a house. I could have cooked eggs about by a campfire, but your brain, your mind collects a bunch of things together and creates a visualization of that, and that's what I'm focused on. Another visualization task you might do is if you imagine the capital letter T, if I ask you how many corners it has, you would all probably be required to use visual thinking to figure out the answer to that. Nobody has stored how many corners are in the letter T, unless you've seen my talk before. Okay? But if you picture it, you can go ahead and count and reinterpret what you've seen. So why is it important? Well, when you start thinking about picturing things, you realize that it happens all the time. Recent studies in daydreaming have found that we spend about 20% of our time daydreaming, 20% of our waking hours daydreaming. And of course, we spend a lot of our sleeping hours visualizing too when we dream. But any kind of hypothetical reasoning, planning for the future, thinking about the past, there's a vast array of tasks that require visual thinking and imagining hypothesized scenarios. There are some scientists, every psychologist likes to talk about what's the one thing that makes humans different from animals. Anyway, one of these psychologists said that it's the ability to picture virtual things that don't actually exist. Okay, and we're all very good at this. So if I have a cup of coffee here, if I were to toss it down into that stairwell, you wouldn't know at a physics level what would happen, but you could all picture basically what would happen, and you'd use your visual reasoning to know that the top would probably come off and coffee would spray everywhere. In these vague terms, you'd have an idea of what would happen. They've also found that if you picture yourself doing sports, you actually are better at doing the sport. This is pretty remarkable. They found this in over 30 different sports. Just sitting there thinking about doing it actually makes you better at doing it. So imagination is terribly important, very, very important, and I'm trying to crack it at a level of detail such that I could get a computer to do it just the way that a person would. So these are the influences. I've actually one should be added to this here, but what constrains your imagination? So if I said I made eggs this morning, you could picture a hippopotamus in the scene. You probably wouldn't. Okay, so what would a scientist use to constrain what would be in that visualization and what would not? Okay, so what we know about the world is this is knowledge. Like to cook eggs, you probably need something to cook with, some kind of source of heat, usually a stove, something like that. You have mental models of how things work, and you'll use these mental models to help know what to put in the picture. But at a simpler level, we've got your visual history, your history of your visual perception, everything that you've ever seen in the world. Okay, so here we are, we're at a talk. I've got a badge on. There's a screen, there's a microphone, I'm tapping at a computer. These are things that you've probably seen many, many times. So when I ask you to picture someone giving a talk, you are likely to put those things in there simply because they've tended to be in those images in the past. All right? And that's what my work focuses on, is how to mine the visual memory to know what goes into an image, an instantiation, and where it should go. The final thing that should be on this slide is probably the task environment that you're in when you're asked to imagine. So when I say imagine eggs, or if you're reading a book, or someone's telling you a story and you picture what's going on, obviously them telling you the story or somebody asking you to picture something is going to influence what you've imagined. Okay, so now I'm going to talk a little bit about some of these constraining things of what science has found. And this is hard stuff. Most people think of imagination as being really hard to study, impenetrable to objective measures, and I will grant you right now that this is not an easy field to be in. But there are ways to do it, and I think you'll be surprised at some of the clever things people have come up with. But the hypothesis of my laboratory is that a great deal of our visual imaginations can be predicted simply through the regularities in our perception. Okay? So if you were to, when I ask you to imagine a cat versus a dog has a higher likelihood of being outside in your imagination than the cat. Cats tend to be indoor animals in this part of the world. I talked to somebody from India recently who said that cats, there are many, many stray cats in India, so perhaps if you've got that different visual history, you'll be more likely to picture them outside than in this part of the world. But if you grew up in this part of the world, a cat might be typically an indoor animal. Okay. So I'm going to talk about some of these constraints here. So the first one I'm going to talk about are the psychological findings. There are a bunch of people in psychology doing research that is relevant here. I'm a cognitive scientist. I use a little bit of psychology, philosophy, and computer science primarily to do what I do. I focus on artificial intelligence, but my lab does run some psychology studies, and I certainly read them and use them. Okay, so one quite famous bit of research is the research and categorization called prototype research, where people have these prototypical ideas of what things should look like. So if I ask you to picture a bird, most people will imagine a small singing bird. Very few people will think of an ostrich or a penguin unless they are trying to be particularly creative or they've got some other reason to think so. But we found this, that in many, many instances, there are these prototypical elements. And this is even true for shapes. If I ask you to imagine a rectangle, you probably aren't going to imagine a square, even though a square is technically a rectangle, and you're probably not going to imagine a rectangle that is 2 feet or 2 inches wide and a mile tall. Okay, that's a perfectly valid rectangle as well, but it's not prototypical. They've even found prototypes with numbers. There are prototypical odd numbers, better examples of odd and even numbers. So when I ask you to imagine a cat or dog or eggs, you aren't going to imagine ostrich eggs or lions. You're probably going to imagine the prototypical cat, egg, etc. There are also canonical views of objects. There's been some research, particularly by Michael Tarr, who's found that there are certain views. So this is what you're looking at right here of me. This is a prototypical view of a person. Okay? It is a valid view. I'm still a person if you're looking at me from the top, and all you can see is my head and shoulders and maybe the tips of my feet. But you don't tend to picture things that way, and that's true for a lot of objects, bicycles and chairs and all these kinds of things. It gets used in the debate over whether we have 3D representations or a bunch of 2D snapshots. But it's relevant for imagination research in that you are more likely to imagine it from a canonical view. This gets particularly important when you're trying to get a computer to do it, because if you've got a 3D model, like in your Google Sketchup thing or whatever, it doesn't really specify what the direction is, where is it supposed to be viewed from, but there is data on that. Okay. So this is a neat little study. This is the most direct view into somebody's imagination I've ever seen. This is crazy. So what they did was, there are some scientists, they showed people white noise. Okay, you see these? Well, it's not really, these aren't pure white noise, but it looks something like that, TV on channel fuzz kind of business. And they showed people 20,000 of these, so it took a long time. And they said some of these have the letter S in them and some of them do not. Now, none of them have the letter S hidden in them. Okay, so people are like clicking, yes, I see it, no, they don't. And people tended to choose about a quarter of them as having the letter S in them. Okay, this is top-down processing, when you're looking so hard for something that you see it, even if it's actually not there. Now what they did was, they only did it for 3 subjects because it's so time-consuming. But when you average the ones they said yes to, you can sort of see the ghostly image of the S that they thought they saw. Okay, so here's the actual average, and you can't see much, but if you clean it up a little bit, you get these things. So these are the 3 subjects. You can see that they all had different fonts, which is really amazing to me. So this is, you're giving them noise, and they're imagining the letter S, and you get this thing with a font. This person's prototypical S apparently does not have serifs. So this does not scale, needless to say. It's torturous to the subjects, but there are ways to look directly into somebody's imagination. Soon we'll have brain scans that allow us to do it even better. Another thing that I would like to do if I can get myself an eye tracker. You've all heard of eye tracking. It's where you have cameras on the eyes and you can see where people are looking. You usually do it with some kind of stimulus to see where people are looking on the stimulus. But what you can also do is have them do it in just darkness, and you describe a scene to them like, oh, there's a dog and above him is a bird that's looking down, and the person will look into the darkness where those things are, and you can get an idea of where everything goes based on where their eyes are going. So you see, we get all these like indirect ways of trying to figure out what's in where things should go and what should go in the image. All right, so there's another body of research coming from linguistics, image schemata. There's also a growing interest in embodied cognition. Now this is interesting. Up tends to be good. Okay, this gets reflected in our language, like things are looking up, or anything up has this metaphor of being good, and down as being bad or sick or dead or something like that. This turns out in our language all the time. It also is part of the folk wisdom of movies and theater. It turns out that good motion, right to left or left to right, depends on the way that you read. So left to right motion is good in this culture, in the English-speaking culture. And if you'll notice, if you watch movies, The Wizard of Oz, Dorothy is almost always moving left to right on the screen. Every time Neo gets into a fight in the Matrix, he's running left to right and his enemy is running at him from right to left. If you go to countries where people write in the opposite direction, it is reversed. Okay, so how does this influence imagination? Well, if you're picturing something that you value as good, you are more likely to imagine it going up or left to right than you are going down. So this would constrain that. And there are all kinds of metaphors. This here I don't claim to completely understand, but I think everyone can intuitively get what's happening here. This is a cartoon by Steinberg in the New Yorker, and we have a tuba blowing its sound, and there's no sound associated with this. Here's a harp noise. It's a visualization of what the sound is. And even though, but I bet you that anybody could match these images to the instruments. I bet we'd have a lot of agreement that this is more like a tuba and this is more like a harp looking sound. Okay, so this is stuff that we're just starting to crack open and trying to figure out what ways to visualize things that aren't even visual, like music. Okay, and this is really relevant to scientific visualization and the growing field of visual analytics and the information deluge that everyone is experiencing in sciences and information technology, where we need ways to make pictures to make sense of things. And if we can understand people's natural inclinations to picture certain things certain ways, then we'll have a much better time creating visualizations that make sense. Okay, so now we're going to talk about mental models. So I mentioned this before here, but part of visualization, in addition to just your visual history, is that you know how things work and you try to use it. This is very hard to model because it is knowledge intensive, where I can use a database of pictures to try to get at a visual history, I actually have to go through and describe the mental model for each object to be able to reason about it. This is a problem that AI has always struggled with. How do we get all the knowledge in the world encoded into a way that a computer can understand? So that's part of why I'm not pursuing it very strongly right now, but it's something that will be necessary to get good visualizations. A computer needs to understand how things work to get the visualizations close to perfect or usable. Now, spatial reasoning happens much more than we knew, say, 20 years back. Okay, a very interesting example is with time. It turns out that people picture time spatially. In our culture, we talk about the past being behind us. All right, so way back then, we use the word back, okay? And they found that when people talk about time, they gesture in accordance with that. So in our culture, when we talk about, oh, back when I was young, they might refer behind them. Future's in front of them and the past is behind them. That might seem completely intuitive to you, but there are cultures where the past is in front and the future is behind. And they think that's totally normal because, well, obviously you can see the past. You can't see the future. That's their explanation for it. And then when they gesture, they do the same way. It's like back in the past, and they'll refer in the front. Now, although it's interesting that the different cultures have different directions for past and future, what's important to me is that everybody represents time spatially. Okay? And if you really want to mess yourself up, try to present a graph where time is going right to left in your graph or something like that. Okay, so we've got these cultural conventions, and more we're finding that there are spatial metaphors for abstract concepts. It appears that we are using our very basic spatial reasoning processing in our minds to make sense of abstractions and other cultural artifacts that have subsequently been invented. Okay, so getting more into the computer science-y part, we've got a bunch of visual databases that we can use to try to collect information about perceptual histories. So this is the ESP game. I think Google might actually own a version of it or something, but this is a game in which it's a fun game that is meant to collect important data. So here's how it works. Two people see the same image, and they're trying desperately to type in the same words, but they can't communicate. They're randomly paired up on the internet. So here people are typing in corridor or columns, and if they write the same word, they both get points, and it moves on. Okay? And so what's great about this is that if two people type the same word, it's probably a good word to associate with the image because you have that agreement. Okay, that's the key insight of this. And after you're pretty sure that the word house is associated with this image, it becomes a taboo word for future players. Okay, this was invented by Luis von Ahn, who's made a bunch of games like this. The whole field is called human computation. Okay, well, what's good about this is that you end up with a database of images with associated labels that you can do image searches over or whatever. But then what he did, he and his students made another game called Peekaboom, which is now taken down because he's replaced it with a game that he thinks is better. But what this is, one person sees a black square, and the other player sees a picture with a word. So here we have a cow, and it's got the word cow associated with it. And this person is trying to get this person to type cow. And what they can do is they click on parts of the image, and they are revealed over here. And this person is desperately looking at the revealed parts, trying to figure out what the hell he's talking about. And when they say, oh, it's a cow, you type cow, and then they get points and they move on. And these words are taken from the ESP game. We know what labels are associated with the images because we got them from the other game. Now we're finding out where they are. So here we know that the cow is roughly here in the image and not in the lower left corner because those are the places that needed to be revealed to get someone to successfully guess it. This is from LabelMe. It's a database that tries to do the same thing but without a game format. It just requires people to volunteer their time to go in and do it. It has two disadvantages. One is that it's not a game, so it's not very fun, so people just have to be willing to – it's not very fun to outline things in an image. So people are less likely to do it. But the other thing is it doesn't have an internal error checking. So people can – and I've seen this – they've – just outlined random sections of the image and given it names, either real labels or just made up words, polluting the database and making it less useful. So when you've got this, in the games, when you make people agree, you've got this internal checking mechanism. Nonetheless, the LabelMe database has a lot of stuff in it. Squiggle is the game that Van On made that is supposed to replace Peekaboom. And what happens is two people see an image and they get a word and they're supposed to outline it. And the similarity of the outlines determines the number of points you get. Okay. Now, and you might have heard of Google Sketchup. This is a 3D image database. Now, when I'm trying to create new images, I'm trying to do it mostly in 2D now. I'm going to be moving to 3D very soon, and I'll be using databases like Google Sketchup and various warehouses of free 3D images so I can populate virtual environments. And I'm going to, let's see what's next. Yeah, okay, so now I'm going to talk about okay, right. So my goal here, what am I trying to do? I'm trying to automate imagination. I'm trying to make a computer program that can create a new image that is realistic. When I say realistic, it makes sense, and it's like the kind of thing a person would imagine. Okay, so if I ask it to imagine a talk, it should know to populate it with chairs, people, a microphone, a computer, a screen, without my having to tell it explicitly to do so. Okay? And the applications are many. Automatic illustration. Okay, this could be important for scientific papers or for entertainment purposes, creating diagrams. Level design for games. Okay, so you've got these games now. Games are more and more games are three-dimensional, and they've got these large virtual worlds that need to be created by hand. This is true in video games. This is also true for movies, and more computer graphics are in movies. There are lots of movies that are completely in 3D computer graphics, and the vast expense with these movies is in artists. Okay, you've got a lot of programming to do, but there's an artist behind every little tree and every element in that design. And if we can automate that, we can get more bang for our buck. And in case all of you are thinking, oh, Jim's trying to put artists out of work, well, kind of. But I will also say that I think it's a shame that we have to wait a year for a new Pixar movie when, if it was automated, we might be able to watch one every night. That is based on what we saw that day. Okay, that's very far off, but I see the world moving in that direction. If we can automate any of this design, it'll be a great win for creating these worlds. And it's not just for entertainment. There's training simulations. The military and medical, lots of people are starting to create virtual worlds for training, and they need to be realistic. And it's a lot of effort to create the world. And once they create the world, it's good for a person maybe once, because then they know the world, and the learning is reduced when they use it again. It's like playing the same video game again and again. But if it can create new worlds every time, then the learning might not slow down as quickly. Okay, I've talked a bit about how we can study it. These are some other things we can do. I'm not going to go into them. They're quite psychological. All right. Okay, so now I'm going to talk about my laboratory and what we've done in the laboratory. So I'm in a cognitive science department. That gives me the great advantage of being able to use whatever methodology I want to try to get at the problem. And with something like imagination, that's very important. So the first and most successful thing we've got is a program called Visio. Okay, so we all can imagine to greater or lesser degrees. One thing that we're all good at is imagining quantitative magnitudes. Okay, let's use size as an example, but it can apply to anything that you can put a number to. So if I ask you to imagine a chair, you will imagine a chair, and you'll imagine that chair being a certain size, probably a realistic size. Okay, but if you go into most 3D databases, databases of 3D models, they don't give you the size, like in feet or something like that. So how is a person able to do that? Well, you have in memory some kind of indication of the size of the object, and you can use that. But we're also very good at imagining things that we've never seen before or never even heard of before. So if I say, imagine a tiny Cheshire cat, you all have no problem doing that. You've never seen, I'm sure you've never seen a cat that was labeled as a tiny Cheshire cat, but you're able to do it. How? So this program is designed to come up with those values. How big is a big tree? How long is a very short rope? Okay, this is what this thing is trying to do. And the program is able to imagine things that it has never experienced in its database. Here's how it works. Okay, so the mascot for my school is the raven, so my student used crows and ravens for the example. So let's imagine that you've seen a whole lot of crows in your life. You've seen a whole bunch of crows, and you've seen them, so they all go into a distribution. So ignore this fuzzy number business on the bottom. Just imagine this as a distribution of size of all the crows you've ever seen. It forms a roughly normal distribution. Now, some of them have been labeled as large. So somebody said, oh, look at that large, that's a really big crow or a really large crow. There's a separate distribution created for large crows. So you can see that it's shifted and it's smaller, and the variance is smaller, other things. Let's also imagine that you've seen ravens. Okay, now ravens are rarer than crows. They're also bigger than crows. So you can see that this distribution is a little bit shifted. But they're rare, and let's say that you've never seen a raven that was labeled as large. You haven't seen enough ravens in enough situations for anyone to have said, oh, that's a large raven. So how large is a large raven going to be? That's one of the basic problems here. How do you know how large to make the large raven if you've never seen a raven labeled as large? Because large, although it seems like it's an objective kind of transformation, it's not. A large mouse and a large ocean liner are very different. The difference between a regular mouse and a large mouse is smaller than the difference between a regular ocean liner and a large ocean liner. So all of these spatial adjectives are dependent on the thing that they are modifying. So the insight that Visio has is that it uses analogy with semantically related things to know how much larger to make it. Okay, so in this case, this is what the program outputs. This is what Visio outputs, an estimated distribution of how large a large raven is. It uses fuzzy numbers to represent, this is a neuron thing here. So neurons have receptive fields, and they increase their firing frequency depending on how close to what it is exactly they're looking for that the stimulus is. So we have this fuzzy number distribution to represent an input. So there are two phases of this program. One is this input phase where it sees a whole lot of things. That's just its experience. It's like you seeing crows and ravens and chairs and coffee cups and improv groups and scientists for your whole life. And then you got the visualization phase where you ask it to imagine a small scientist or a long person. And every time it sees something, it represents it using these fuzzy numbers here. It's not very important. If you want to ask me about that later, I can talk about it. But it's a distribution over different numbers and their memberships. So what happens is it looks through the database. If you ask it to imagine a large raven, it looks through the database looking for something semantically similar. So you've seen crows, you've seen buildings, you've seen ocelots, you've seen chairs. Well, what is most like a raven? Well, crow. So we use the WordNet semantic similarity. There are a bunch of semantic similarity measures out there, and it finds the thing in memory that is closest to it that for which we do have a large distribution. Then Visio finds the mathematical transformation to turn one distribution into the other. So we've got all crows here and we've got large crows over here. How do we turn the distribution of all crows into the distribution of large crows? That's a mathematical transformation. Then it applies the same transformation here, and then it generates an imagined distribution of large ravens from which you can imagine a single large raven. Okay? And it has some really neat properties. I'll give you some qualitative results and then go into the quantitative results. So in this image, we can see that it is shifted. What I mean by that is that the ravens are bigger than crows. So we would hope that the large ravens would be bigger than the large crows, and indeed we can see that that's true. So that's good. Okay, here we have differences in variance. So here we can see that the ravens have a smaller variance than the crows. Crows have more variety. If you need a good example, dogs are a great example. Okay, dogs have enormous variety. An adult male dog, depending on whether you're looking at a Chihuahua or a Mastiff, have a great variance in size compared to pigeons, for example. So you would hope that in the imagined large ravens, you would have a smaller variance. And indeed, you do. These are actual results from Visio. Now, when I say they're actual results, these are actual results with made-up numbers. We don't have numbers of how big crows really are. I'm working on another project to get those numbers, but right now, these are just made up. It's just to demonstrate that the reduction in variance is maintained. This also works with high variance. Here we have the ravens are a very high variance, and we see that the resulting distribution also has high variance. Okay, so if we're going to look at the, I'm sorry, this is probably not readable, but these are the quantitative results here. And basically, we show that the take-home message of this is that the error rates for the estimated sizes are small. So here we have trying to imagine a thin cat, a medium cat, or a thick cat. Okay, this is taken from the Peekaboom data. So remember I talked about Peekaboom where people isolated where things were in an image. What we did was we calculated the height-width ratio, or width-height ratio, because it's distance independent. The problem with these is we don't know how big something is in an image because we don't know the distance from the camera. But the ratio should stay the same. And what it did was it retrieved dog. Dog is the most similar thing in the memory of all these things here. We had about 10 things. And then it estimated the ratio. And then we did this with raven, person, dog, pole, building. And so what it's doing is you're asking it to imagine a high width-height ratio cat, but it's never seen anything labeled as such, and it's guessing what that ratio is going to be. And the overall average error rate is 6.98%, which I think is small. It's hard to know what to compare it to, but it's fairly accurate when you compare it to the actual width-height ratio. And another interesting thing is that it greatly depends on the number of objects in the database. So there are lots of people in the database. There are very, very few crows and ravens. And when you have more things, it gets better. This should be no surprise to anybody in this audience. But there are lots of applications where just adding data makes it work a lot better. The Peekaboom database only has 57,000 images with an average of 12 labels each. When we get into the millions, I'm sure that these error rates are going to go down even more. So that's the Visio program. And we're going to use that. We're going to use this thing because we need to know how big things are, right? So when I ask my computer program to imagine an office, it's going to need to figure out how big everything in that office is going to need to be. And if I say imagine a large tree, it should know how large to make the tree and come out with an actual number so that I can put that in the image with a really concrete size. It also works in a less interesting way, but it does work with prepositions. So if you ask for an airplane above a mountain, it's going to give you a different number than a bird above a tree, because an airplane should be much higher above the mountain. Okay, so even words like above, prepositions like that, also are context dependent on what they're referring to. Okay. We also have a need for understanding prepositions in human beings. So when I say that something is above something else, you might think that, oh, that's easy. Just look at the axis, and if it's above that axis, then it's above. Well, it's not that simple. So let's see here. It could be that a cup on that rack over there is technically above this podium, but no one would describe it as such. Okay. I might be, to the right of my university, but who's going to describe it this way? Okay, so when something is that far away, it's less likely to be called above. So there's this sweet spot of above the podium that sort of starts here and looms up like this. And you have to figure this stuff out by looking at data collected by linguists and psychologists and stuff to figure out what above really means. So anyway, we've got one project where we're trying to make computer programs that emulate this kind of detection. Okay, so what it does is we've done above, below, and close to, and occlusion. and try to figure out what it means. So I actually have my students do this in class projects. They have to pick a new spatial detector that's never been done and create a detector for it in my AI class. And they have to read the literature in cognitive science and figure out what these prepositions mean and then try to replicate it as best they can. So here's above, and close to is an interesting one because it depends on the size of the frame. It turns out that these two things are perceived as closer than these, even though it's the same physical distance, because people do use the size of the frame to help decide whether something's actually close to something else. But this kind of stuff is really important because when you ask the computer to imagine something, you might use these prepositions. So if I say imagine a clock on a wall or a cat on a sofa, those are different, right? Particularly in English, where on has these two meanings. A clock on a wall is against it and flat up against a wall. In different languages, these are different. These spatial prepositions are all over the place. Korean has a different word for fitting loosely and fitting snugly, for example, right? So these are English specific. I don't want to say that these are general human kinds of things. But I got to start somewhere. I'm going to start with English. If I can get a computer to imagine things from English input, I'll be very happy. So we're trying to create these models of spatial prepositions. I'm going to be presenting this work at the Diagrams Conference up in Portland in a week or two. Here's occlusion, okay? Figuring out if two things are covering one another. And in Peekaboom, this is an interesting problem because all we have are point clouds. So here we have the red dots for A and the blue dots for B. How do we know which one's occluding what? Well, one's going to be in front of the other one, but if B were in front, we probably wouldn't see A, so A is probably in front. There are three different kinds of occlusion we try to calculate, and you can see where we extend and try to estimate where these things are going to be and come out with an occlusion metric. And this is good if you want to say that a cat is in front of a tree or something like that. And we've actually applied this to make a little mini search over the Peekaboom database, which is only 57,000 images. But what you can do is you can say a hand above a plate, and it actually returns hands that are above plates in a way that's realistic with the way a human would, which I haven't seen before in an image search. Okay, so we're mining Peekaboom and we're mining LabelMe and probably Squiggle too, and anything we can get our hands on for relationships between things. All right. Cooccurrence is a big one. If a computer always appears in the image with a monitor, or does so 30% of the time or 90% of the time, that's very important for our system to know. Because if you ask it to imagine a computer, it's got to imagine more than just the tower, right? It should imagine a desk and a keyboard and a mouse and everything. And cooccurrence can get us that. Okay, very simple. You look at all the images in the database, you see what tends to be in the image with computers. Not only that, but because we have information about where they are in the image, we can know where they're supposed to go. So we look at like the angle and the distance, and we can know that the keyboard tends to be below the monitor, and we know by how much. And we know by how much we can feed that into Visio, so for any given image we can figure out exactly how much that's supposed to be. And we can populate a 2D image with what's supposed to be there, okay, using probability and all this kind of thing. Not only that, we analyze those things with those spatial detectors I just talked about in the previous slide. So we know what's above, what's below, what's close to, what's far, what's occluding, what's not, what's in between, okay? So that when we know which ones are examples of that, so that when we ask the system to imagine things like that, it can say, oh, I know what they mean by in between. I'll do that. You don't need to be able to read this. This is someone else's work that's, we're moving into 3D now, okay? WordsI is a program out there. I'm trying to get my hands on it, but it's been difficult. But according to the paper, what you can do is type in something like this. An orange umbrella is on the small patio table. A window is behind the table. A small red umbrella is 5 feet behind the table, etc. You go through you give this textual input, and it generates this 3D image. It can also do lots of fun things. If you say, like, the devil is in the details, if it doesn't know what details looks like, it just puts the word. So it has a picture of a devil and the word details sort of surrounding it. It's fun. So this is related work, and we're basically re-implementing this and trying to do something like it, so that we can create 3D things. Now, there are a few. We're trying to find a good platform that we like, and if anyone has any ideas, I'd like to hear about it. But we want to use some kind of open source virtual world to put these things in. There's a community called OpenSim, which is kind of a open source clone of Second Life, and it's got its problems, but it is open source, and we're thinking of having our computer programs generate virtual worlds that are usable by OpenSim. However, the people who work on it are mostly interested in socializing, so there's not a whole lot of physics. When you touch something, basically the avatar's hand goes out and a dotted line goes from the the finger to the thing. So for modeling human behavior, it's limited at this point, but there's always hope for open source things. They get better and better. But we want to actually create virtual worlds. To me, I think it would be really fascinating to be able to tell a computer system, imagine a virtual world that has a lot of mushrooms and darkness, and just have it populate the entire world just as a human designer would. So those are the things going on in the laboratory. I also want to say with this co-occurrence and co-occurrence in images and knowing where things are, we're also trying to improve object recognition, because object recognition right now does not tend to use context. Okay, so if it detects a computer and a mouse and a monitor, it doesn't look for a keyboard. We know to do that. Okay, but if it looks like a penguin on a desk, it's going to say, I detected a penguin, ignoring the fact that it's unlikely that there's a penguin on a desk. Okay, so but with this database, this model of what should be in images, we know what it's likely to find. So we're trying to modify an existing object recognition system to give it better results. We make an advisor based on this imagination model. So to conclude, the imagination is terribly important. People use it all the time. I firmly believe that we'll be spending more and more of our time in virtual worlds, 3D virtual worlds. As the hardware gets better and as computer processing gets better, we're going to be spending more time in virtual environments. And there'll be a great need to automate the creation of these things, both for conferencing and virtual travel, entertainment, training simulations, and all of this, and all the way to making movies. If you invite me back for a talk in 20 years, I'll tell you how the automatic movie making is coming along, but that's a tough one. But personally, I'm very excited to see what kinds of images that these computers are going to create for us, and what they're going to put in. At this point, we can only imagine. Thank you very much. We have a few minutes for questions. Happy to take some. Yes. So the latest version of Adobe Photoshop. Yeah. Do you want to use a mic for the questions?
Okay, so the latest version of Adobe Photoshop has this impressive feature they call content-aware editing. Have you seen this in action?
Yes, I have. I've seen the demo.
Yeah, the demo. And so they take a tree and delete it, and or a road and delete it out of the scene, and the thing fills in the rocks in a reasonable rock pattern. And so I'm wondering, what's going on there? How much does it, bear on your research? And, how much is the system just sort of extrapolating maybe some, fractal patterns from the nearby area versus kind of recognizing a bit more what's going on?
Okay, so what he's talking about is part of a broader field that's including something called photo stitching, where you can, there's a lot of work on this. You could take like two photographs and like stitch them together to look like it's one photograph. And there are even systems where you can say, wedding kiss, sailboat, tree, and it goes from a database and it puts them together and makes an image that actually looks relatively coherent. I'm going to be using that technology for creating 2D images. So the short answer to your question is it's very relevant. So removing something out of context, what it does is it finds some pixels elsewhere in the image. In Photoshop, it only uses that image. Okay, I was just at SIGGRAPH. At the SIGGRAPH kind of people, the people doing research at the technical talks there, use databases of images to give them more power. But what it does is it finds some pixels that are similar and it fills it in with those. I don't see how that's going to scale to 3D. So for the 2D stuff, I'm definitely going to use that kind of thing. And I'm in conversations with people. Unfortunately, they all have a user interface, and I need it to interface with my AI. So I'll probably have to get a programmer to work on that for me. But yeah, I follow that research because it's really important.
So they call that stitching in general?
Photo stitching is, yeah, putting two photos together in a way that makes sense.
So you might have your favorite search engine that you can type words into, and it'll come back with lots of images that you can run correlation analyses on. For example, Bing. And to what extent are you able to use these kind of commercially available products to do some of the things that you're working on?
I haven't thought about it a lot, but I'll tap dance a little right now. I can type in cat and get a bunch of images with cats in them. What I don't get is, for each image, what else is in that image. So if I could type in cat and then get a whole bunch of images of cats, but also a list for each image of what else is in that image, that would be great. Most image search engines, to my knowledge, use surrounding text to know what's in it or what words are relevant. And that might be different from what's actually pictured. And what I ultimately need is which pixels are a cat and which pixels are a doorknob. And there's a slightly different goal with image search, right? If you type in victory, you might want somebody like going through a finish line. But well, actually, I would use that too. Actually, if somebody wanted to picture victory, I guess I would want that too. So that's relevant. But that's the reason that I haven't really looked into it. Do you see what I'm getting at, or is there a way around that? I don't know. Can you put in an image and get the word? Can I type can I like query with an image and get what words are associated with it? With any search engines now? Would you use the mics for the recording reasons?
I don't know if this is entirely relevant, but I read some article that in Korea they're doing this thing with ads, that to serve ads against it, they're trying to understand what's in the image. So they have a whole database worth of images, and they're reading the image directly and not the text surrounding it for visual context. So they see that there's a boat in the image, and they're trying to use other images and match it against it and say, that there is a boat in this, and I don't know,
using computer vision?
Yeah, using computer vision.
Oh, I'd love to see that.
Yeah, if you give me your email, I'll send you the article.
Okay.
Yeah, there you go. Cool.
It's hard to remember, but it's there.
And just as a note, it might not be something that's available through the interface of search engines, but if you actually talk to the people at your favorite image search engine, I'm pretty certain that there'd be a way to access the data that you're talking about, because it's implicit in the way the databases are structured.
Right. Okay, that'd be great. I would love some kind of collaboration with a big search engine in that way, because right now the 57,000 images are not enough. And I just saw a talk at SIGGRAPH where they said, when we tried it with 20,000 images, it sucked, and we went up to 2 million, it suddenly worked. And I have no doubt that this is going to be one of those instances. Yes.
I'm kind of fascinated by those games you showed, and I confess my ignorance. I didn't know about these things, but how popular are they? How much is that being used on the internet?
I don't know, but it's generated a lot of data. If you go to gwap.com, GWAP, it's games with a purpose, okay? They've got a whole bunch, Tagatune, and there are a whole bunch. And I've just created one that I haven't published yet, but to try to get sizes of things and distances. But yeah, if you're gonna waste time playing a video game, play a game on GWAP, because then it's not a waste of time. You're helping researchers like me and helping the world out. Got time for another question or two? Dr. Tullio?
Yeah, so I was wondering about how bound some of the stuff coming out of your lab is as to what's sort of like bounded in reality, because the images that you're using, are they all like photographs of real things? Are they drawings? So if you ask me to imagine a big raven, or a big cat, I might imagine something that's fairly plausible. If you ask me to imagine like a giant cat, then that would be something that you probably wouldn't have a photo of. Does that make sense? So would if you pose something like that to your software, would it be able to come up with things that aren't bounded by, the potentially real world input that you've given it?
No. Right now, the best it could do, and it's not even totally working yet, but it will be soon. If you say a giant cat, it'll take a regular image of a cat and make it big. And that obviously is not ideal. A large, like a person that's 30 feet high, well, I mean, physically probably wouldn't be able to walk at all, but to be a good visualization of it would have to have thicker legs and this and that, move more slowly. But yeah, we don't have the ability to do that yet.
I see. So you'd also have to have sort of like the physics and how that would actually work out in a 3D world.
Yeah, that would be a lot more work. And the other thing is that this database of images they're images from the web. They're not even necessarily photographs. So there are cartoons, there are logos, there are all kinds of things. So we have in my students, when they have to make this above below detector, they have to look at the Nike swoosh and a tagline and say, is the swoosh occluding the tagline? Those are the kind of things it has to deal with. But we can specify only photos. But really, the way I look at it is we do look at logos in real life, and those do influence our visualizations. And we're using images from the web as a proxy for human experience, which is questionable. But until we have people walking around with cameras on their heads and recording everything that they've ever seen, and we get them all tagged, that's what we'll be working with. I think we take one more. No more? Okay, thanks everybody for coming.